Welcome back. Let's continue with our discussion on reaction mechanism. The goal of reaction mechanism is to answer the question, how does a chemical reaction take place? And then to explain how factors like temperature, concentration, catalyst affect the rate of a reaction. So we looked some of that last class in the last video when we talked about how the rate of a reaction depends on the number of effective collisions, and these collisions in turn depend on the activation energy and they depend on the right orientation. So let's continue with this idea of how reactions happen. We think chemical reactions do not happen in one step, but instead reactions happen in a series of elementary reactions on a molecular level. By an elementary reaction, we mean it is just one step in the whole reaction mechanism. So for example, if we look at this reaction, 4 moles of HBr reacts with 1 mole of oxygen to produce 2 moles of water and 2 moles of bromine gas. The rate law that is experimentally determined is known to us, but we don't think that at the moment of the effective collision, you actually have 5 molecules, 4 of hydrogen bromide and 1 of oxygen colliding to produce these products. We think that it is more likely for a collision to be between 2 molecules, so 1 molecule and a second molecule. This is more likely than 3 molecules colliding together or more than 3, 4 or 5 molecules colliding together. Just like on a highway, we think that it is more likely for 2 cars to collide, and yes, then you can have a pile up after those 2 cars have collided, more cars can join, but it is very unlikely that at the very same instant 3 cars coming from 3 different directions would collide right then. So we think this is less likely, and we think that's the same thing that holds true for chemical reactions as well. So for example, the proposed reaction mechanism for the reaction that we looked above, instead of 5 molecules colliding at once, we think that this reaction happens in a series of elementary steps. So each of these steps is a reaction step. So first HBr and oxygen combine to form this intermediate HOOBr, and then that intermediate is used up. So it's formed here and then it gets used up in the second step and so on. The slowest step in a reaction mechanism is called the rate determining step. And an analogy here is the assembly line. So for example, if some of us were getting together to make, say, sandwiches, one of us was buttering the bread, the other person was adding tomatoes, and someone else was adding the lettuce. The rate of production of these sandwiches, of course my drawing isn't the best, would be dependent on whoever of us, if there are 3 people working, would depend on the slowest person. So similarly, the rate of a reaction also depends on the slowest step. A question that I get asked most often in class when I say this is, can there be 2 slow steps? Well, see, slow is a relative term. So we are saying the slowest step. So there could be 2 steps that are slow, but it is highly unlikely that 2 steps would have exactly the same rate of reaction. Okay, maybe in theory that is possible, like it's hard to rule that out, but it's highly unlikely. So nothing comes to my mind when I get asked that. Okay, so to recap, what we have said is that a chemical reaction does not happen in a single step. Usually it is made up of a series of elementary steps, and those elementary steps are more likely to have a bimolecular collision, a collision involving 2 molecules, maybe termolecular, but this is highly unlikely to have a multimolecular collision. And then we have said that of these elementary steps, the slowest step is the rate determining step. Now the thing to keep in mind about the reaction mechanism is that the reaction mechanism is a proposal. It is a theoretical construct. Yes, it is possible to verify it in a lab if you could isolate some of the proposed intermediates, but in general, at this stage, you can also propose a reaction mechanism, but any reaction mechanism that you propose must meet some criteria. So, one of those criteria is that the sum of the steps in the reaction mechanism must add up to give you the overall equation, and the theoretically obtained rate law from your proposal must be identical to the experimentally derived rate law, because if they are not the same, then something else is going on in the actual reaction. Your proposal is wrong. You need to go modify the mechanism and come up with another series of elementary steps that could give you the same rate law and would add up to give the same overall equation. So then comes the question, okay, so how do you determine the rate law from elementary steps? So here are the rules for that. Let's just take a second and read this, and it will become clearer when we actually try to come up with a proposal. So the rate law from the rate determining or the slowest step can be written following these rules. Rule 1. You combine the concentration of the reactants with the rate constant K. Rule 2. A coefficient in front of a reactant becomes exponent for that reactant. And rule 3. The rate law must not have any intermediates. Catalysts are okay. So let's go to the slowest step here, and let's maybe rewrite that for ourselves. So the slowest step is HBr plus O2 forms HOOBr. So let's follow these rules. Combine the concentrations. So we would say rate equals rate constant K, and then combine the concentrations of the reactants. So we write HBr multiplied by concentration of oxygen. So I followed rule 1. Rule 2 says a coefficient in front of a reactant becomes the exponent for that reactant. So the stoichiometric coefficients are the implicit one, nothing is written. So that means that the order for these reactants also becomes 1, 1 each. Rule 3. The rate law must not have any intermediates. Catalysts are okay. Okay, well, I realize we did not define what intermediates are. So maybe let's take a second and do that first. An intermediate is any species that is produced in one step but used up in another, and a catalyst, on the other hand, is a species that is present at the start and end of the reaction. Okay, but the catalyst is usually not present in the overall equation. An intermediate is also not present in the overall equation. So then let's go back and look at these steps and see if we can find catalysts and intermediates. So let's use purple for intermediates. As the name intermediate suggests, it is something that is formed in this step and then used up in the next step. Do we see any other intermediate? Well, we see HOBr is formed in step 2 and then is being used up in steps 3 and 4. Anything else that is formed and then used up? No. And the rate law we have figured out from the slowest step is here. KHBr times O2. Are any of these intermediates? No. HBr is the reactant, O2 is the reactant, so it meets that criteria. Rule 3, that it does not have any intermediates. Is there any catalyst present here? Well, is there something that was present at the beginning and was also present at the end? No. So then there is no catalyst in this mechanism. Now, for this mechanism to be correct, the theoretically obtained rate law, which is here, must be identical to the experimentally derived rate law. So if you actually went into a lab, let's find out what that experimentally determined rate law was. Oh, wait, we have already told us that the experimentally determined rate law is this. So since our theoretical rate law agrees with the experimental rate law, we can accept this mechanism and say this is a probable mechanism. So I think the first two rules are clear enough. Let's look at rule 3, the one that says the rate law must not have any intermediates. Catalysts are accepted. This has a fancy name. This is called the steady state approximation. The idea here is, or the assumption is, that there is at least one intermediate in the mechanism that is used up as soon as it is generated, so its concentration does not change. This will become clear in a second. So let us look at a reaction. 2NO plus hydrogen forms water and N2O. And here is a proposed reaction mechanism for this. So there are two steps, step 1, step 2. One is fast, second is slow. The first part says name any intermediates. So the definition of an intermediate is something that is produced in one step but used up in another. Well, produced in step 1, used up in step 2. Are there any catalysts? The definition of a catalyst is something that is present at the start and the end of the reaction. Is there something like that? No. So there is no catalyst. Let's figure out the rate law from the rate determining step. The rate determining step is the slowest step. So let me figure out the rate law. Rule 1, combine the concentrations of reactants with the rate constant K. Let's do that. So I will say rate equals K times concentration of N2O2 times concentration of H2. And then step 2 says write the coefficients in front of the reactants as exponents. Well, they are both the implicit or implied 1, 1. So that's my rate law. But wait, there is a problem. The problem is rule 3, the rate law must not have any intermediates. Catalysts are okay. Well, N2O2 is actually an intermediate. So we cannot have N2O2 in the rate law. So now we need to do something else to get rid of N2O2, and this whole process is called the steady state approximation. So pay attention to it. We'll maybe do a couple of examples so it makes sense. So what you do is, because this was the slowest step, you now go to the fast step. And this step is fast because it is happening in both. Sorry, it is the other way around. The causality is the other way around. Because this step is fast, it is actually happening in both directions. So as soon as N2O2 is produced, some of it goes back and breaks up as NO. Okay, and because there is, and we haven't studied equilibrium yet, but there is an equilibrium established between these two species. And the definition of equilibrium, just so you know now, is the rate of the forward reaction is equal to the rate of the backward reaction. Okay, and in this case, because this is a fast reaction, let me write this again. So NO on both arrow facing to both sides forming N2O2 is the fast reaction, which means there is one step that is forward, going in the forward direction, and one reaction that is going in the backward direction, and at equilibrium this rate of forward is equal to rate of backward reaction. So let us write both the reactions separately just so everything is clear to us. So the forward reaction is this, and the backward reaction is N2O2 going, I'm going to write it as backward, forming 2NO. So what is the rate from this forward reaction? Well, the rate forward is, you write K and we'll write K forward, and then you write the concentration of the reactant, which is NO, and you raise this to this exponent, which is 2. So that's my rate of the forward reaction. What is the rate of the backward reaction? So again, rate constant B backward, I write N2O2 and I raise it to the implicit coefficient 1. Okay, so this is my rate forward, rate backward, and I've just defined for you that at equilibrium rate forward is equal to rate backward. So let me set those two equations equal to each other. So Kf NO squared is equal to rate constant backwards N2O2 concentration 1. Okay, and keep in mind I was trying to get rid of this N2O2 term from the rate law because this is an intermediate. So basically what I'm doing is I'm trying to solve for this concentration of N2O2, which means I can bring this Kb down to this side. So I get K forward over K backward times NO squared is equal to N2O2. Okay, let me call this equation 1, and I can sub this value of N2O2 in here. So let's do that. So my rate for this reaction becomes, there was some K I had written, multiplied with K forward, K backwards, NO squared times H2. Now yes, this looks like a lot of one constant, then second constant, third constant, but really a constant means a number. So if the first constant was, let's say, 1.2, the second constant was 3.1, 4.6, whatever, eventually you could compute what number they eventually ended up being. So we can simply write one constant K. Okay. Again, this does cause some grief to students in the beginning, but really think about it. If you did solve the value of K, you would actually only come up with some numerical values, and you could compute, you could multiply and divide them and still be left with a number. It's not a variable. So your rate law becomes K NO concentration squared H2 concentration. So this is our rate law, and now this rate law meets the condition that it does not have any intermediates in its expression. Okay, let's take one more example of steady state approximation. Okay, so here's a proposed reaction mechanism, and we are asked to figure out the rate law from this reaction mechanism. So we see this is fast, this is slow. So I will use my slow step to write the rate law, and the rate would be written as rate equals K, let me say slow, multiplied with H2 concentration, multiplied with concentration of I, and then I'm going to raise them to whatever is the coefficient in the balanced chemical equation. So 1 for H2 and 2 for I. So that's my rate law from the slowest step. Now I go and check if this rate law has any intermediates. So let's see, does this mechanism have any intermediates? Well, this I is produced in step 1 and used up in step 2. So that makes I an intermediate. So I cannot have this intermediate in my rate law. I need to get rid of this intermediate I. So what will I do? Steady state approximation. I go to my fast reaction, and my fast reaction would have rate forward would equal rate backward. The forward rate would be K forward times I2, and the coefficient is 1, so raised to power 1. And the backward reaction, and if you need to, you could write the backward reaction again for yourself. So this is the backward reaction giving I2. So then the rate for this backward reaction would be, you would write the constant Kb, and you write the reactance, which is I squared for this 2 in the balanced chemical equation. Okay, and then you have to remind yourself or keep in mind what was it that you were trying to isolate for. So you're trying to isolate for this concentration of I squared. So let me do that here. I get concentration of I squared is equal to the rate constant for the forward reaction, I2, divided by the rate constant for the backward reaction. So let me go ahead and plug equation 1 into the rate law. So then my new rate law becomes rate equals K from the slow step. H2 is okay because it is a reactant, raised to power 1, and instead of concentration of I squared, I will write this as K forward, K backward, I2, concentration of iodine. Okay, so this was nascent iodine atom, and this is iodine molecule, which, as you remember, your Hofbrinkel are the 7 diatomic molecules. Okay, so now here maybe this is more clearer that you can sort of combine all these constants into one constant, and you get rate is equal to K H2 I2, and that's the rate law that you get from this given mechanism. of course, this rate law needs to agree with the experimentally determined rate law, and only then this mechanism would be an acceptable proposal. So before we leave, let's look at two more questions. So this first question is a multiple choice question. They've given us a reaction, they've given us a rate law, and they have given us a proposed mechanism. And they're asking what are the relative rates of step 1 and 2. Is one slow, 2 fast, is 1 fast, 2 slow, and so on. You really, like I said earlier, we will not consider this option of both slow or both fast. Okay, so let's just cherry pick for a moment, and let's say, okay, this is fast, this is slow. If that was the case, what would be the rate law? So the rate law comes from the slowest step. We write K for the slowest step, then we write the concentration, so ICL concentration times HI concentration, and we raise them to the stoichiometric coefficients here, which are 1 and 1. Well, that's the rate law I get, and then I would have to go and cancel the HI, come up here to find the rate law. Well, it doesn't seem to look like this rate law. So I know that this option is not correct, and of course, by elimination, that sort of tells me that A must be the right answer, but let me show you why A is the right answer. So if we said that the first step was slow and the second step was fast, then from the slow step, which is the first step here, my rate law would be rate equals K times concentration of ICL times concentration of H2 raised to the coefficients here, which are 1 and 1. So that actually agrees with the given rate law. So that's why I know that A is the correct option in this multiple choice question. Then another kind of question, which is bringing together both your potential energy diagrams that we did last time when we were doing activated complex theory and your reaction mechanism of having elementary steps. So this question says, for this graph, determine the number of elementary reactions. Well, you're seeing that the reactants start here, and these are the products, and then the reactants collide, they form something. So this is an intermediate, then that intermediate undergoes some reaction and you get another intermediate, and then this finally something happens and you get products formed. So the number of peaks tell you the number of elementary reactions. So in this case, there are 3 elementary reactions. Sometimes a question will say mark the intermediate. So now you know that the troughs, the lowest points on these curves are the intermediates, and the transition states would be here. So you would have transition state 1, transition state 2, transition state 3. Okay. Let's go to the next part of the question. It says, is the reaction overall endothermic or exothermic? So remember, because the products have less energy than the reactants, energy has been lost to the environment. So this is an exothermic reaction. And then the last part says, what is the rate determining step? The rate determining step is the slowest step. And how do we know from a potential energy graph which is slower? The one that has the highest activation energy. So let's go ahead and sort of eyeball the activation energies. So this is the activation energy here. In the second case, the activation energy is from this intermediate to its transition state, and the activation energy here is from intermediate 2 to its transition state 3. So which seems like the longest line? This is sort of a qualitative question. You're not quantitatively measuring how much larger the EA is, but you can sort of tell that the EA is the largest in this case, right? So then step 2 is the rate determining step. Okay. So I have shared on the class Brightspace a lot of kinetics questions, and then I've also shared solutions to those questions. So please try them first yourself, then check yourself with those solutions, and if still something doesn't make sense, please come and see me during office hours. Okay, good luck. Take care.